Hi, this is Murat Kahveci. The title of my talk is Advancing Chemistry Education Research, Dual Process Theories, Learning Objects, and Student Response Systems. This presentation has been prepared for European Conference on Research in Chemical Education, held in Barcelona in 2016. I will talk about advancing chemistry education research as a field, the problem, affective domain, education technology for rich interactivity, conclusions and acknowledgements, and I will end with my talk with my contact information in case you have recommendations or questions. Chemistry education research as a field is gradually advancing at university level. There are two distinctive groups of experts in chemistry education community. One group is made of chemists in pure science. Another group is composed of chemistry educators. I called group 1 and group 2. And just to refer to each group, how do groups 1 and 2 contribute to the chemistry education research as a field? Group 1, this group of experts conduct their research in chemistry and take teaching role for chemistry courses close to their expertise. This group generates new knowledge in the field of chemistry and creates new learning domains for the next generations. Of course, group 1 has more history as opposed to group 2. Chemistry education is a new field, and it's not well established as opposed to chemistry in science. Chemistry educators teach introductory level chemistry courses and all levels of pedagogical courses at universities where there is a degree offered in chemistry education at graduate level. Research-wise, chemistry educators conduct social and behavioral research on teaching and learning of chemistry. So this is the field that we are talking about. Cooperation of groups 1 and groups 2. So one group generates chemistry, which means scientific information. The other group helps the dissemination of this information to young generations. So when we talk about chemistry education research as a field, we are talking about the depth and breadth of issues in chemistry and pedagogy as a total effect. To advance chemistry education research, it is imperative that both groups of experts need to cooperate mutually. There is a report by European Union released in 2007. It's called Science Education Now, a renewed pedagogy for the future of Europe. On the basis of this report, European Union started a new funding schema. In 2007 they decided, and the first level of funding was released in 2008, and that report produced a European-wide action, actually, towards inquiry-based science education. I'm not going to talk about the funding scheme, of course. I'm going to talk about the problem that report clearly expresses. The number of young people entering universities is increasing, but they are choosing to study fields other than science. In consequence, the proportion of young people studying science is decreasing. In 2003, the total physical science graduates in the US dropped by 12% in comparison to 1995. The The same comparison for Germany is even more dramatic because there is 50% loss. When looked at from a gender perspective, the problem is even worse, as in general, females are less interested in science education than males. Only 1/3 of the population, which means mathematics, science and technology graduates in EU, 27 countries, was female. Surprisingly, the same result is valid for the US case. Instead of 31.2%, it's 31.1%. So, as already mentioned, there have been huge investments by European Union towards science education, and they choose to invest for the seventh framework. They choose to invest in inquiry-based science education, the dissemination of best practices. Likewise, to support this action, the direction of chemistry education research should align the focus towards alternative and innovative methods for teacher training and practice of chemistry teaching. In response to the need for innovative methods in chemistry education research, I propose two directions. One, affective domain. The second one is education technology for rich interactivity. The reason for affective domain is that because affective domain is less emphasized as opposed to cognitive domain. And the report, the ROCA report or the EU report that I already mentioned, specifically mentions that students are less interested. So there is a problem with students' interest, motivation towards science. We have to understand it, why they are choosing different fields than science-related fields. So something is going on, students' learning experiences, and so it's probably not a positive effect, it's a negative effect. So we have to understand how learning occurs, how human behavior is affected by affective domain. Once we understand this, the second step that I choose to mention is to use education technology in a more engaging way. So to increase the interactivity in chemistry classrooms. When you choose to have highly interactive classroom environments, research says that the output of the students are greatly better. They are performing better in terms of their grades. So when I talk about affective domain, I mean the factors that are the determinants of decision-making process and their implications to chemistry learning and teacher training. In social psychology, dual process theories are developed in the past 3 decades. However, we don't really use this approach, those dual process theories in chemistry education research context. So I think it has lots of potentials. So what is dual process theories? An attempt to explain how behavior is generated through impulsive and reflective systems. So there are dual systems. One system is labeled as impulsive and the other is reflective. When we say reflective systems, it's more of cognitive processing, and the impulsive is more of automatic and fast. So the reflective side is slow and it takes extra effort as opposed to impulsive side. But we have to understand which systems are affecting students' attitudes or affective sides more. So when we adapt dual process theories into the chemistry education context, this adaptation simply leads one to consider more affective aspects than usual and less cognitive aspects than usual. Because the majority of chemistry education or any science-related field is focusing on cognitive aspects with testing and with the way that we assess student learning. It's more cognitive than their attitudes. So again, if you ignore affective aspects, then you start to assume that students are black boxes, and you just, with educational system, you just give some input and you get output, and you don't know what's happening inside the student. So that's perhaps what we are missing currently. So if you start to understand how affective aspects are influencing students' behaviors, then I would say chemistry education research will be more human-friendly. Dual process models share a subset of beliefs about the quest for knowledge, opinions, and understanding. Duality refers to little or maximal cognitive effort while arriving at a sense of knowing. Sense of knowing might happen in either top-down or bottom-up models. When we say top-down, we lean on prior knowledge, heuristics, stereotypes, expectancies, scripts, and schemas. When we define bottom-up, which means we are expending a great deal of time, effort, and mental energy in systematically building decisions, beliefs, and a sense of knowing. Neither strategy guarantees a bias-free response. The two are just distinctive paths of arriving at knowledge. Strack and Dodge, they wrote a very lengthy article and with lots of information about a special case of dual process theories. They called it reflective-impulsive determinants of social behavior. In that paper, they determine how behavior is actually physically developed by both systems, both reflective and impulsive systems. In this model, social behavior is the effect of operation of two distinct systems of information processing, a reflective and impulsive system. The systems can be specified by different principles of representation and information processing. Both systems operate in parallel. However, there is an asymmetry such that the impulsive system is always engaged in processing, whereas the reflective system may be disengaged. The reflective system requires a high amount of cognitive capacity. Therefore, distraction, as well as extremely high or low levels of arousal, will interfere with its operation. In contrast, the impulsive system requires little cognitive capacity and may control behavior under suboptimal conditions. Elements in two systems are connected by different types of relations. In the reflective system, elements are connected through semantic relations to which a truth value is assigned. In the impulsive system, the relations are associative links between elements are formed according to the principles of cognitivity and similarity. There exists a finely common pathway to overt behavior in the impulsive system that may be activated by input from the reflective and impulsive system. This pathway consists of behavioral schemata of varying abstractness. If the schemata is achieved above a certain threshold, the behavior will be executed. So, this is the impulsive and reflective system and how behavior is generated under those influences. So there are parallel operation. In brief, reflective-impulsive determinants of social behavior attempts to integrate cognitive, motivation, and behavioral mechanisms. Social behavior is the result of several determinants that may operate in accord or conflict with each other. Affect and emotion are understood as products of the reflective and impulsive system. When simply put, the way that I see this theory is that if both systems are working in parallel operation, and there is an asymmetry, as mentioned earlier. If students quickly think that, or feel that, or intuitively decide that they don't understand, they don't want to invest any more energy on any concept, they will stop learning. And the output is just negative in terms of educational expectancies. So, understanding the student behavior from affective side, I propose to use education technology for better interactivity. When I say interactivity, I mean learners' interaction with other learners, with the material that is used by the learner, and with the teacher. So the more interaction one individual has, the better learning will be as the outcome. So when computing power and gets more and more advanced, and reduction of their cost to individuals, then it's more available to the public at large. With education technology, we can create rich interactivity and self-study environments. And those environments can be adaptive to individual needs. I'm going to talk about two emerging technologies, and one is specifically easy to deployment, and it's called learning objects. Learning objects are actually a technological tool that includes all kinds of media, including text, images, movies, and set of questions and interaction with students. So it's delivered through web, and you can have lots of logic loops, and you can have lots of student to system interaction, and teachers can interfere this and help students understand topics of interest. But the main idea is that learning objects can be designed in such a way that students just learn themselves, and the system adapts to students' learning needs based on certain assessments that is done automatically by the system. This can be easily developed. In fact, I have such an experience with a physical chemistry education context with a small project. The second technology that I want to mention is integration of student response systems, or clicker technology. These are very simple tools mediated by computers, and many instructors nowadays use it. However, it has to be effectively used in order to achieve the instructional goals as expected. Those student response systems provides instructors immediate feedback from students, and from student side, teachers can design some questions, simple questions that are easy to answer by the student, or in a small group of students in 1 or 2 minutes, and that will interrupt the presentation, one-way presentation from teacher to classroom, from student to teacher, and back to from teacher to student as a immediate feedback. These systems can gather lots of information from students in a short period of time, and if it's multiple choice type of input from the student, then it can generate graphs and distributions of the classroom, so student knows where his ideas stand, and teacher just reacts to the classroom based on the distribution of students' ideas. So it's both way, and from professor to student, student to professor. It's very, very informative, and from the student side, it's an engaging technology. Again, coming back to learning objects, Learning objects are able to exploit various educational technologies, including those based on web and virtual learning environments. Very unique feature of learning object is that they are used and reused, and they are very fragmented. So a picture can be defined as a learning object, but a unit in a book can be defined as a learning object as well. So so a learning object has a goal, a teaching goal, and that teaching goal can be achieved in different times of the classroom in classroom instructional setting. So once generated, many learning objects can be just chosen from a library, and teachers can use it in a very quick way, and it's multi-platform or interoperable in a more technical way, which means it can be used in Android devices, it can be used in Apple devices, and as long as you have a supporting internet browser. Learning objects support high student interaction with chemistry content through adaptive feedback loops and sustain student engagement through self-study. My experience with learning objects is the following. I have completed a project between 2012 and 2015, and that project was about certain physical chemistry topics, and I developed 3 learning objects on how to understand 3 physical chemistry topics. Those classes are taken by third year chemistry students, so they are majoring chemistry. In my experience as a chemistry educator, I am interested in already some computer programming. However, many things are graphical and open source, so it means any professor can generate learning objects easily. Besides, there are many databases of learning objects. You can just either purchase or obtain them freely. Learning objects in a more technical label are known as SCORM packages also, and like Moodle, I use Moodle system. It's a learning management system, or Blackboard, both, or some other. There are many versions of learning management systems that in common they all support SCORM packages. You just install like a software, so any package can be distributed to students very easily. When a student uses the system, then the system in the background records many information from the student, like the time the student spends on each page, and the answer that is given by the student is recorded by the system as wrong or right, and the system can even grade a student performance based on a point system. So it's very it has lots of potentials. You can include animations, you can include movies, you can include a series of reading passages, and you can include some questions that is answered by the student, and the system just gives the answer right away. So it's student just tries an answer and the system just gives a feedback, true or false, and the reason for that. So you have to just enter all of these information before student can interact with this. So if you are preparing those kind of systems, it's very easy actually, but it's demanding in the sense that you have to create a scenario, and you have to think that you are just instructing in the classroom, and a student may ask you a question and you may just answer in a different way, and etc. So it's based on experience, and if you teach a course over and over again, you will have lots of teaching experience, and then you can import these teaching experiences in the learning objects while designing them, and many students can use it, many teachers can use it once it's developed, so it can be used by thousands of people. Another strength of learning objects that I want to mention is that you can build a sequence of hyperlinked documents. So one student can just learn one piece of information, and the system can be programmed in a way that if the student is performing well, then you can skip some parts of the learning objects, or in other case, if student is not performing well, then system automatically takes a different path and student just repeats the cycle again and again, but with a different level of reading and practicing. So it's really it can be programmed in an adaptive way. So each individual takes different time to complete and different needs based on their background. So one student can complete 5 cycles, one student can complete 1 cycle. So in that sense, learning objects can be really adaptive. In my experience with the project that I am talking about is that especially physical chemistry as a subject, it's very difficult for students because it involves mathematics and many abstract chemistry concepts. When they start to read a physical chemistry book, normally they are very thick, over 1,000 pages, and they have less hour than they should, normally in theory courses, I mean. And it's very, very cognitively demanding. A system like learning objects helps them because they can interact with the computer, and which they may not have the same opportunity in the classroom. And they interact with the computer, and they immediately see if they understood it or they guessed it correctly or not. So they can just spend more time or just proceed to the next topic. So the system actually helps them a lot. But in my experience, again, I don't see many professors are using this kind of platforms just because they are, I don't know, busy too much, or because they don't know the technology, or they don't know the availability of this kind of platforms. So that's why it's important that we should remind that learning objects are really good learning tools for students. Students' response systems support in-class interaction, and it's really ideal for face-to-face instruction with large classrooms, over 50 or so. So you can gather large data sets. Normally, student response systems are used for multiple choice type of questions because the system can analyze it and show the system can just mark is correct or wrong if it's multiple choice, and you can even give grades to your students because each keypad or each clicker has a special ID, and that ID can be just known by the teacher and associated by the student's name. But in my research, I used student response systems for gathering open-ended data. So my keypads were like QWERTY, had QWERTY keys like a computer, and I was asking open-ended questions rather than asking only simply multiple choice questions. And I used student response systems to gather from large group of students to gather their reason for a specific question. So normally when you ask multiple choice questions, you just get the result, get the answer for the question itself, but you don't get the reason. It's difficult to get the reason. And my next comment is from, again, chemistry education research point of view. We often use two-tier instruments. The first tier, the first level of this kind of instruments, diagnostic instruments, you ask direct question and you get the scientific answer. In the second level of the question, you get you ask the reason, the scientific reason. Why did you choose this specific answer? That reason and the first level answer must both be correct, and this kind of instruments are difficult to develop because you have to interview with the students in order to get their reasons. And of course, this kind of instruments leads you to common alternative understandings or alternative conceptions of scientific phenomena. So in literature it's called misconceptions. And these instruments are just very practical, that you can just ask a multiple choice question and ask an open-ended question to like 50 students. You get just one sentence from each student, and you can easily see variety of understandings, multiple understandings, or alternative understandings of the same phenomena, and you can either label alternative or scientific or aligned with scientific understanding. So student response systems are really handy in that respect. As a conclusion, the reflective-impulsive model explains the behavior and its determinants in a sophisticated manner. And once you understand how behavior is affected by affective elements such as motivational factors or intuitive ideas or interests, then as an instructor and as a researcher in chemistry education, you may choose to focus on more affective elements than usual. Use of new technologies such as learning objects and student response systems will increase the interactivity in chemistry classes, which will allow more chances to have different assessment tools, faster and more in-depth data collection processes. Overall, this will increase the quality of the assessment, the quality of the instruction. I'd like to thank the organizing committee of European Conference on Research in Chemical Education because they kindly supported this keynote lecture. And I'd like to take Çanakkale 18 Mart University Scientific Research Programs. And they funded aforementioned two projects. One is physical chemistry education and learning objects, and the other is impact of instruction interactivity in chemistry education. Thank you for your time. Any questions or remarks, please contact me via email at mkk8653@my.fsu.edu